A very good morning to one and all. I welcome you all for the session number 29. In this session, we will learn how to apply Lagrangian method in deriving Newton's law of motion. In the last class, we have derived Lagrangian equation of motion using D'Alembert's principle, which is given by d by dt of dou L by dou Qj dot minus dou L by dou Qj is equal to Qj. This is a generalized form of Lagrangian equation where L is equal to T minus V, where T represents kinetic energy and V represents potential energy. For a conservative force, Lagrangian equation of a motion, where Qi is equal to 0, then d by dt of dou L by dou Qj dot minus dou L by dou Qj is equal to 0. Note that we have derived this equation for an holonomic case. The learning objective of this session is to understand how we apply Lagrangian equations in deriving Newton's equation of motions. By the end of this session, we will come to know how Newton's equations of motion can be arrived using Lagrangian equations of motion. Problem. Motion of a single particle in Cartesian coordinates. The position of a particle under motion can be represented using Cartesian coordinates. So let x, y, z, t as a function of time be the Cartesian coordinates of the moving particle, and x dot, v dot and z dot be the velocity of the particle of mass m along x, y and z axis respectively. We know that the Lagrangian equation in generalized coordinates is given by d by dt of dou L by dou Qj dot minus dou L by dou Qj is equal to Qj, and also L is equal to T minus V. I know its velocity, I know its mass, so then the kinetic energy expression is given by of m x dot square plus y dot square plus z dot square. However, for a moving particle, the potential energy is assumed to be 0. Expressing this Lagrangian equation into its force components, we arrive d by dt of dou L by dou x dot minus dou L by dou x is equal to Fx, which is the force component along x-axis. Similarly, d by dt of dou L by dou y dot minus dou L by dou y is equal to Fy, which is a force component along y-axis. Similarly, d by dt of dou L by dou z dot minus dou L by dou z is equal to Fz is the force component along x-axis, z-axis. Now to apply this equation, I should know L term, which is T minus V, that is kinetic energy as well as potential energy. Next, I need to differentiate that L term partially with respect to generalized coordinates, that is x dot, y dot and z dot. Similarly, I need to differentiate that L term with respect to Qj where Qj can be x, y and z. So L is equal to T minus V. The kinetic energy of the moving particle system is of m x dot square plus y dot square plus z dot square. The potential is equal to 0. The first I need to differentiate dou L by dou x dot. So on differentiating, I get mx dot, and dou L by dou x is equal to 0. So substituting d by dt mx dot is equal to fx. Differentiating mx dot will arrive at mx double dot is equal to 0, which is the force component along x-axis. Similarly, differentiating L with respect to y dot, we arrive my dot. Differentiation of dou L with respect to y will get 0. Therefore, dy dt of my dot is equal to fy, or my double dot is equal to fy. Similarly, we arrive at expression mz dot is equal to fz. In general, these are all the forces fx, fy, fz can be rewritten as m r dash r double dot is equal to ifx component plus ij fy component plus k fz component, that is equal to f. So therefore f is equal to m r double dot, which is nothing but Newton's second law of motion in terms of acceleration. That is, f is equal to mass into acceleration. Now you see that how the same Newton's laws of motion, using kinetic energy and potential energy, we arrive Newton's second law of motion. That is the beautiness of Lagrangian equation. You arrive at different equations of motion just by knowing its kinetic and potential energies. So in this session, we learned how to derive kinetic energy and potential energy for a constrained motion. And also we derived Newton's laws of motion using Lagrangian equation. So let's have small MCQs. Question number 1. Degree of freedom for a particle in motion is, if it is moving in a space, so the degree of freedom is 3. So option is A. Question number 2. The coordinate chosen as a generalized coordinate for a particle in motion. Do remember, if we specify it is moving only in one direction, it can be x, y or z, or it can be all of the above. So the option is y. Small correction, that B option should be y. Question number 3. The total kinetic energy of the particle is of m into x dot square plus y dot square plus z dot square. So which is, I don't have any expression like that. So answer is none of the above. Question number 4. Potential energy for a particle in a motion is, assume it is 0. So option is D. Question number 5. Lagrangian equation for a particle in motion is L is equal to 1 by 2 m x dot square plus y dot square plus z dot square. So the option is answer A. Question number 6. Dou L by dou x is equal to, we see that Lagrangian is independent of x. So dou L by dou x will be equal to 0. So the option is C. Question number 7. Lagrangian equation of motion for a particle in motion is, it is mx double dot plus my double dot plus mz double dot. So option is answer A. Mx dot represents, know that mass multiplied by velocity will give you momentum. So option is answer B. To be specific, motion along x-axis. So that is option is C. Mx double dot represents, it is a force term along x-axis. So the option is answer C. So in this session we learned, Question number 10. Dou L by dou Z dot. This is m z dot. So the option is answer C. So in this session, we learned how to arrive at Newton's second law of motion using kinetic energy and potential energy in Lagrangian equations. So if you know kinetic energy and potential energy for a system, then you can derive its equation of motion. Hope you enjoyed this session. Thank you all.